Hello, my name is Bob D. Hilster and I am your particle model guru. Today we're going to talk about electrolysis, which is the third video in a series of videos covering chemistry. So previously I've talked about water being the universal solvent, and that's important because in all the cases I'm talking about, water is used to create the electrolyte. Set it up for the battery. Today it's going to set it up for electrolysis. I'm going to do a kind of a summary a little bit. These videos are about chemical reactions. Water is a universal solvent used in many chemical processes. Not all. There's other solvents, and normally we add a compound to the water, and it changes. The G2 gravity changes between the atoms. The water atom sneaks in and kind of infiltrates the compound that you're putting in the water. It changes the G2 gravity such that it weakens it for both the compound and the water, and then the vibration takes over and shakes them. It literally shakes them apart by vibrating. And when it's all done, you've dissolved the compound in the water and you have an electrolyte. It's a chemical action which involves the changing of the G2 force in water and the compound in vibration, and that's the chemical reaction. And we get that in batteries, as I did last time, and today we're going to do it with electrolysis. In the case of electrolysis, a battery is going to emit G1 particles and cause a chemical reaction. Okay, and this reaction is mechanical. The particle model claims that a chemical reaction is mechanical. Just kind of summarizing and keep making the main point here. Okay, looking at electrolysis, there's a lot of uses of electrolysis. They're listed all over here. What's used in the production of some difficult metals. They can help produce aluminum, sodium, calcium, and magnesium. You use potassium hydroxide to produce chlorine and sodium hydroxide. You can use electrolysis for electroplating with chromium, nickel, gold, and silver being plated on the electrodes. And today it's being used to generate hydrogen for fuel and for electrifying of fuel cells, generation of electricity for fuel cells. And the author had a comment from the who posted this, had someone post a comment that a couple of more common uses of electrolysis that are normally overlooked. Rechargeable batteries. There's electrolysis there, and making electrolytic capacitors. That's why they're called electrolytic, because it uses electrolysis process. A lot of uses. This is a typical apparatus, a Hoffman type apparatus that's used as a demonstration, as students use it to actually separate and generate oxygen and hydrogen when they use electrolysis to do that. You have one tube with a platinum electrode in it, another tube with platinum electrode in it. You have a feeding tube where you feed in one common electrolyte. You have a salt bridge, and when you connect the battery, you get electrolysis, and oxygen accumulates on one side and hydrogen accumulates on the other side. Now this is a little bit more complex, but it tells you something about the fact that you just don't connect these things and get the same thing every time. This is a chart that shows the voltage applied to the apparatus. And this tells you about the electrolyte. The electrolyte can be acidic or be a base. A pH of 7 is neutral, and you get different reactions. If you use an acidic electrolyte, you get this reaction when you want to get hydrogen, or you get this reaction when you want to get oxygen. And of course, up here you have a positive charge, and down here you have a negative charge. So positive charge will give you oxygen when you have either acid or base, and you get the same thing. So you can get this action with only one acid, all of it being acidic, or all of it being base, but you have different reactions. Okay, the electrodes. The DC power supply is connected to two electrodes in these two plates, typically made of an inert metal such as platinum, stainless steel, or iridium. They're the same. Both electrodes are the same material. If they were different, it's possible that they would try to act like a battery, although I could not find where they would fit in the electrochemical series, what voltage they might have associated with them. But they're the same, and they're basically inert. If they're inert, if they have a voltage, it's not going to be very strong. Okay, so let's look at the standard explanation. This is really kind of complicated, but I'll try to get through it. On this side, like starting on this side, you have water and you put potassium hydroxide. I'm using potassium hydroxide as the, you can use other hydroxides, but in this case I'm saying potassium hydroxide splits and gives you the potassium ion and the hydroxide ion. And water will split. Water splits, here's the water, and it will split into also the hydrogen ion and the hydroxide ion. That's the chemical reaction that happens before you even put the battery to it. On this side, we have we add hydrogen sulfate, excuse me. And so you get the hydrogen, water splits into the hydrogen atom and to the sulfate ion, I should say, hydrogen ion, sulfate ion. At the same time, water splits into hydrogen ion and a hydroxide ion. So that's the chemical reactions happen immediately, and they're happening presumably on a continuous basis. Then what happens is you connect the battery, and electrons are pushed, they say, into here and escape and combine with the hydrogen. You combine an electron with a hydrogen ion. That's what this is supposed to be. Gives you a hydrogen atom. Two hydrogen atoms combine to make the gas when they're pushed. They say that on this side, the electrons are being pulled out. The battery pulls, however it does that. I don't know how it pulls, but it does, and somehow removes the electron from the hydroxide ion, leaving a oxygen atom and a hydrogen atom, or maybe a hydrogen ion. I'm not clear on that point, but two oxygen atoms combine to make oxygen. You get the oxygen over there. So they say it pushes electrons and you get them combining to make hydrogen, and you pull electrons here and you get oxygen. The second thing that actually happens apparently is through the porous diaphragm that keeps this generally separated, but not. The hydrogen must be, since it's negative, gets attracted to the positive, and these hydrogen ions are positive get attracted to the negative, and that's presumably how they say they're moving. They have to move from here to here, and these move over to here. to support this production of hydrogen and oxygen. Okay, well, I'm going to use the same diagram and try to talk through the particle model. In the particle model, what I would expect is that when you the action before you connect the battery is the same. I'm not disputing that. Those are chemical reactions that happen. So you get all these ions there. But when you connect the battery, in the particle model sends G1 particles moving at high speed that scatter off of the platinum electrode. And when they scatter, they come out and they become orbitals of the ion. When the G1 particle becomes an orbital of a hydrogen ion, you make a hydrogen atom and get the gas. Quite simple. So this process is the same thing that I'm agreeing, except that I'm saying it's released at speed c, becomes an orbital to make the hydrogen atom and the hydrogen gas. Somehow in the particle model, these things have to move. Now, but when they do move, let's assume that they do for the moment, and you have over here you have somehow you got to pull these off. Well, the particle model doesn't pull anything. The particle model can push this hydroxide ion. It can hit it. Now, if it hits it hard enough and in the right way as an ion, possibly what happens is it shakes it loose. That's the only thing I can think of, is that because the G1 particle is going to go through and around, and as the G1 particle comes through and around, it can hit this item. Possibly both of them are knocked loose, setting this ion to separate into an oxygen atom and a hydrogen ion. I guess it doesn't quite sound right, but the oxygen atom combines with another one to give you O2 gas. So that's the process of combining. Over here, the G1 particle gets trapped by the hydrogen atom and makes a hydrogen ion and makes an atom. Over here, it's got to get knocked loose somehow, and the only way I can see is it gets knocked loose by the G1 particles coming across. So actually everything kind of works. You can explain it that way, except the motion of this. The hydrogen ion moving this way, the hydroxide ion moving that way. How does that happen? So I'm assuming that this is the way the particle model works, and there is a flow, and there's going to be a lot of flow. As you know, the battery keeps putting out more and more until it gets a stable configuration. The real question is the same question I had on the battery. How does set this up to flow this way? And it's difficult to explain because of the complexity. If I had a nice clear explanation, I'd tell you. I don't, all the way back to one of my videos on the fact that there are two gravities, I suggested there are two gravities because of the way the forces push light as it goes through a prism. But yet I could not explain why the forces are always perpendicular. It would seem to me they ought to be pointing towards the center and not perpendicular to the surface, and I can't explain that. And these are equally difficult to explain. I'm going to have to assume for the moment that there is a way to explain that. There's more to be learned here, and however, this is what happens. So you get a lot of G1 particles coming around, flowing through the electrolyte up and back, and you have a simple circuit that way. So how do the hydroxide ions get over here and the hydrogen ions get over here? So we're going to look at it vertically. I'm going to flip it vertically, And what you have here, I'm going to contend what you have here is nothing more than G1 gravity going from here to here, where the G1 particles are pushing on the hydroxide ion. They're heavier than the hydrogen ion, and so the hydroxide ion will fall towards, I say fall because I got it flipped, but fall towards the positive terminal, letting the hydrogen ion to float up. You got, I'm claiming a gravity gradient here. The pressure gradient is is just like the hydrogen ion and the hydroxide ion are like an atmosphere that end up with a pressure gradient. Hydroxide comes here, the hydrogen ion up here, and the process continues. So the movement is strange. You can understand why you can push these heavier ones here, but why would hydrogen move that way unless it's floating up this way? Okay, and then we move on to back. I'm going to put it back. Horizontal G1 gravity. I've mentioned this several times, not so much here. In some other presentations I've made, I've talked about horizontal gravity, and I always get a little bit of a snicker, but horizontal gravity in terms of the particle model is a reality to me. It's a real feature of the particle model. And if you know anything about Henry Cavendish's experiment where he tried to find the mass of the Earth, in the process of doing that, he actually discovered the value of G, of the Newtonian constant, gravity constant. If you look at his experiment, if you try to explain his experiment using the particle model, you have to talk about horizontal gravity, because that's what he used. He negated vertical gravity by his setup, and he used horizontal gravity to do the experiment. So it may sound funny, but you have horizontal gravity causing a pressure differential between the plates where the ions, hydroxide ions, go to the left, and the hydrogen ions float towards the right to continue the process. So the conclusion is the standard model uses plus ions are attracted to a negative electrode, and negative ions are attracted to positive electrode. And they continue their idea that there's an electrical current flow from the positive to the battery to the negative, and a chemical current flow with the ions flowing back and forth. That's their answer. Particle model, I claim the G1's already moving at high speed. G1's flow through the electrolyte, setting up a G1 gravity there. The G1s scatter and become orbitals of the hydrogen ion, and the G1 gravity that's between the plates, they push the hydroxide atoms towards the positive terminals, and the hydrogen ions float towards the negative electrode. It's all mechanical, no positive, no electric. I'm going to take a brief moment to talk about something a little bit different. Normally, when you hear the standard model talk, they talk about four forces. There's the weak force, the magnetic force, the strong nuclear force, and the nuclear weak force. I've listed some here. The weak force is G1 gravity, which is the loss of G1s through the Earth. You have a G1 field passing through the Earth, you get scattering, and you have loss of G1, setting up a G1 gravity field around the Earth. Very simple gravitational process. Strong nuclear force is controlled by G2 gravity. G2 gravity keeps the nucleus together, keeps the G1 orbiting around the nucleus, and that's the strong nuclear force. In between, they normally talk about magnetic field. In the case of the particle model, the G1 flow around the magnet is controlled by G2 gravity. So it's the G1, the ones that are the force, but behind it is the G2 controlling it. Same thing with the chemical, saying there's a chemical force here where G1 gravity inside of between the plates in electrolysis is controlled by the battery and the G2. The battery provides the G1s, and G2 gravity causes the flow between the plates. So we have really more than, if you want to consider this a force, you may argue the point, but that's essentially what's happening in the G2 model. Haven't talked about nuclear weak force at some point. Hopefully I will get to that. So my name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.